the screen and the stage is yours, Nuno.
Thank you so much for the lovely introduction. So with no further ado, let me give you this lecture in a nutshell. So I will try to cover the issue of poor reproducibility of animal research and its main consequences. I'll try to address some of the sources of bias that affect validity and reproducibility, with a particular focus on animal research, and then by the end wrap up by suggesting some measures that include planning, pre-registry, and reporting, and improved reporting to minimize the problem of low reproducibility of research as a whole and animal research in particular. So when we talk about reproducibility in animal research, I am talking about reproducing results in similar circumstances. So typically, or in some cases, reproducibility is mistaken for translatability. So moving from animals to the clinical setting, to humans. Here I will cover reproducibility as our ability to reproduce results in animals in the same animals in a different lab or different lab settings, or even by the same person in a different point in time. But I will mention the issue that reproducibility is a prerequisite for translatability. So starting with a quote from one of my favorite movies of all time, as Morpheus said to Neo in The Matrix, "You take the blue pill, the story ends, you believe whatever you want to believe, but if you take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. If you're all here, I will not give you any choice. You're all taking the red pill. So what if I told you that most published research findings are false?" Well, this was actually a groundbreaking paper by John Ioannidis. Recently has fall from grace from downplaying the problem of the COVID pandemic. So don't get too attached to your heroes, but he has been largely in most of what he claimed in this paper vindicated, even though he faced enormous backlash at the time. So he stated that it could be proven that most claimed research findings are false, that most research findings are false for most research designs and for most fields, and that claimed research findings may often be simply accurate measures of the prevailing bias. Of course, extraordinary claims require extraordinary evidence, especially because we trust published science to be reliable, given that we use a scientific method, papers are peer-reviewed, and science is self-correcting. So what could possibly go wrong? Famous last words. So we should question these assumptions. We do use a scientific method, but more often than not, we have very poor experimental design with low power studies. There are errors in statistical analysis, exaggeration of results, selective reporting. So meaning that you just report part of the data, the one that better fits your own theoretical model. Hacking, fraud, and misconduct. And of course, none of this should matter because papers are peer-reviewed. The thing is, there is very high subjectivity in peer review. If you've ever submitted a paper for review, you've known that reviewers may disagree completely. So you might have a reviewer that will think it's fine, some other reviewer that would say, well, okay, this is okay-ish, but you should have mentioned this and do that other test or something else and rephrase this, and then it's more or less publishable. And then you'll get reviewer 3 that will completely trash your study and say, well, this is rubbish. So there's very high variability in this appraisal. there is very poor training in statistics of reviewers. Actually, as editors, do editors know whether any given reviewer is trained in experimental design and statistics? I know I wasn't when I reviewed my first manuscripts. So I got sent manuscripts for review. I was really happy that someone considered me an expert, and I thought I was knowledgeable enough, and I tried to do my best, but chances are I missed important problems because I wasn't trained enough in experimental design. And actually, there is very little time for proper review. So then Quintana, the other day, launched a poll on Twitter asking how much people took, how much time people took to carry out a proper review. And some said 3 hours, some said 5, most said 5 or 8 hours. And I was like, okay, I'm maybe doing something wrong because I usually take 2 full days to review a paper properly. So to actually read it through, look at the methods, write a proper review. So I don't think even 8 hours, who has a full day to carry out a review? So what this means is that it will affect the quality of the review. Also, some journals will tend to favor sexy results. So the more outlandish for some journals, the more likely it will be to be published. But of course, the more outlandish, the more it contradicts the established evidence, the more likely it is wrong. So there's also bias against negative results. We'll be discussing this in more detail shortly. And there are no instructions for reviewers. Again, I have reviewed almost 50 manuscripts right now, and I never got an editor saying, well, you should take into consideration this and that to perform your review. And of course, also there's often not enough detail in papers to make an informed appraisal. And the raw data is not provided. And there's also the issue of fake peer review, which is connected to fraud and misconduct. But none of that should matter, because science, at the end of the day, is self-correcting, right? Yes, the thing is, it does take too long. There are very few confirmatory studies, and because science builds on previous knowledge, the errors will tend to accumulate. The failure to replicate other labs results are usually not reported, so the community misses that very valuable information that there is no reproducibility when one tries to reproduce someone else's results in their own labs. And of course, we do that because there are no incentives to publish negative results or confirmatory studies. So how reproducible is preclinical data? This is from Friedman et al. From 2015. And they did a short review of some reproducibility efforts, some from industry, some from academia. And what they illustrate here is that at best, whether a study is reproducible or not, the main findings will be of 50%. So it's the probability of tossing a coin, basically. But in some cases, as the Begley and Ellis study showed, irreproducibility, mind that this is not reproducibility, but rather irreproducibility, can go as high as 89%. So roughly 11% of studies in a given field being reproducible. How wasteful is this? So they actually did the math, and for a 50% irreproducibility rate, they calculated that in the US alone, this meant around $28 billion wasted. So imagine the whole world combined, how much waste in financial terms this represents. This is a breakdown of one of the studies that were here, the reproducibility effort by Bayer. And they looked at 67 studies oncology, women's health, in cardiovascular disease, where they were trying to find whether reported effect on some of these conditions in animal models was reproducible in-house. And they found that in only 1 out of 5 cases, so 21%, the data was fully consistent, the published data was fully consistent with the in-house data. And that in around 2/3, there were major inconsistencies to the point that they didn't even carry out with the rest of the studies, because they found so many inconsistencies that they didn't finish the study. So most scientists have experienced failure to reproduce, and here immediately you can notice a bias. Which bias is it? That it's more likely for scientists to fail to reproduce some, or at least to report failing to reproduce someone else's studies rather than their own. But still, in most cases, failure to reproduce results, either our own results or someone else's, is roughly 50 or more %. And in this very survey of more than 1,500 scientists, 90% think that there is a reproducibility crisis. I tend to disagree. I do not think there is a reproducibility crisis. A crisis is an acute problem. It is a chronic, systemic, pervasive problem. So we know it's bad. So we will find plenty of publications stating this. So systematic reviews, systematic reviews of systematic reviews, meta-analysis, opinion papers that have accumulated in the literature telling us how things have gone sour. The thing is, this knowledge is becoming mainstream. So you'll see news reports in newspapers such as the New York Times, The Guardian, or The Economist on how irreproducibility science often is. Even in John Oliver, and actually this segment it hurts. It's very painful to watch, but it's brilliant. So if you do have the time, do watch it. And to this I say, don't make them right. And who's them? For instance, in our case, who perform animal experiments are the animal activists that oppose animal use. And I give the example of the European Citizens Initiative, the ECI Stop Vivisection, because it represented in a way a shift from condemning animal research from an ethical perspective alone, from a moral perspective based on the harm caused to animals. And these people were coming from the animal rights perspective that regardless of any potential benefit, it would be unethical for them to carry out experiments in animals because animals were not ours to experiment on. But here it represented this shift to also, or mainly, considering animal research as fraudulent. And they were based largely on the fact that most research in animals, or at best 50%, is irreproducible. The thing is, of course, all of science, so survey research in psychology, there are tons of issues with cell culture research, of course, and many of us are very well aware of that. But of course, this served their narrative, and they did manage to be listened to by the European Parliament and the European Commission, who had to actually give a formal reply to it. Also, anti-vaxxers, scientists, the nihilists, science denialists in general, with the dangers that we all now are seeing against vaccines, against scientists, against established science. So, are reproducibility and translational failures connected? One example I like to give is from the reproducibility effort made by the amyotrophic lateral sclerosis Therapy Development Institute, or ALS-TDI, because they selected 50 drugs that had shown promising results in animal models, in particular one animal model, which was the one that was available at the time, which was the Supraxis dismutase mouse mutant. And they decided to retest all of these 50 drugs. Why? Because they ultimately failed in clinical trials. So they wanted to know what had happened. And they decided to do it properly. So this is the reported effect in survival, in terms of increasing survival from a number of drugs. At the top, you can see riluzole, which is the only one that at the time was approved for treating ALS. And on average, it extended survival by 2 months. And you can see that doing it properly, so with adequately powered, fully randomized blind animal tests, the effect that they actually observed was more in line with what had been observed in clinical trials. This raises, as we've seen, financial issues, financial problems, because the millions and billions spent in these flawed animal research studies, but also and especially in the clinical trials, are problematic, but also they're problematic from an ethical point of view. There was a waste of animals in these flawed experiments, and most importantly, we were recruiting patients and giving them false hope based on flawed animal data. And I cannot see how this is ethical in any way. So the conclusions are that preclinical findings cannot be expected to translate to clinical practice if they cannot be reproduced under similar circumstances in the first place. The thing is, we do not know the extent to which irreproducibility of animal studies affects translatability. Irreproducibility prevents informed appraisal of actual predictive validity of preclinical models because of confounding effect of methodological errors and biases, let alone whether the animal model has any validative predictivity or not. Okay. The thing is, we do know is that if they're not reproducible, we cannot expect them to be translatable. We can't achieve the same results in the same mouse, in the same mouse model, or any other mouse model in different circumstances. How can you expect to change species and also find the same results? But what are the causes of this poor reproducibility? So Dorothy Bishop suggested there were 4 horsemen of irreproducibility. It's always men. It's always men everywhere. In this case, men on horses, blame them. So the 4 horsemen of irreproducibility were in her view, were publication bias, low statistical power, p-value hacking, and harking. And I will focus on these, but there are many others. So there are many more horsemen. Actually, my fellow geeks will recognize those as the Nazgûl. So there's very poor research quality control, so low internal validity of the studies themselves, with lack of blinding and location concealment, no randomization, poor anamorphic conditions that will affect scientific outcome, other uncontrolled sources of bias that I do not have the time here to cover, the misidentification of the experimental unit, likewise, and fraud and misconduct. Most publications tend to downplay fraud and misconduct and say it plays a very small part in irreproducibility. I used to say that, I used to believe that, but if you follow, for instance, Elizabeth Twitter account, you'll find that there are several cases of image duplication and what we would definitely call misconduct in research. And we are finding more and more the further and the closer we look. So it's not looking good. And also something that I do not have the time to discuss here, and don't get me started on it, is the flawed reward system in science. But I will tell you that if number of publications, which was a metric to define whether you were productive as a scientist and whether you were a good scientist, when this metric became the goal, and once, as a rule of thumb, once every metric becomes a goal, then it stops being useful as a metric, because it will, in a way, it will corrupt everything else from to some extent, at least. So publication bias, one of the horsemen. How does it work? So this is more or less just an illustration. So let's say that there is a 10% chance that any given compound will have an effect. So you'll find differences between treated and untreated groups. And you look at 1,000 compounds, so you would expect that you would detect the 100 compounds that actually have an effect, the ones that work. So you power your experiment to 80%, you set your alpha to 0.05, and this is why we deem any p-value below 0.05 to be, quote unquote, a significant difference. And what you see on the left would be more or less what is true, what one would find in nature. But because we have set these conditions, and if there is no other source of bias from just random variation alone, you will miss the effect of 20% of them, because you've powered your experiment to 80%, and you'll find a number of false positives. So 5% of the drugs that do not work would actually be found to have some effect just from random variation alone. The problem is that, as you can see on your right, the 36% of the positives are false positives. So assuming, of course, 10% of finding of there being a true effect. So what you see on your left is what is quote unquote true, and what you see on that circle is the distortion of truth caused by publication bias, which is the favoring of quote unquote positive results. I actually think we should completely ditch this negative finding, positive finding way, because it has it is value loaded. I don't think it actually there's positive or negative finding. Any finding, if it's achieved via proper experimental design and proper analysis, is a good finding. Either is good data or poor data. So we should do away with the whole positive negative finding thing because of this. So negative results are going into the negative results drawer. I won't have much time to cover the issue of the low statistical power, but basically statistical power in animal studies is low when not enough animals are used to find an effect of a given size. And if we fail to detect said effects, we are wasting animals. So using fewer animals than needed is not in line with the principle with the 3 R's principle of reduction. Why? Because we are wasting those animals, regardless of how few we are using. Of course, we are wasting animals, time, and money that should be invested in proper research. There's also the winner's curse, which is if you have low power, meaning if you have a low likelihood of finding an effect, if the effect is there, then if you find it, what does that say about your finding? So this is called the winner's curse. If the experiments are underpowered and an effect is nonetheless found, the quote-unquote lucky scientist who makes a discovery is likely cursed by finding an inflated estimate of that effect. The thing is, if this quote-unquote cursed researcher finds an overestimated estimate of the effect, and 9 others that say find a true effect, which is there isn't any, chances are the one who found the exaggerated effect will be more likely to get his or her research published. Also, the overall false positive discovery rate increases when power decreases. How does this work? Well, the same diagram I showed you, but instead of 20% of compounds with an effect that we failed to find, we failed to find 50% of them, which are the ones you see in red. And the other ones are the 5% of false positives. And what this means, if for a 50% power, is that 40% of the positive findings reported are actually false positives. You can see in this what these are called rain cloud plots. These were done by Andrew Stewart. Is that the higher the sample size, the more precise your estimation of the true means will be. So here are comparisons between two groups where there is no effect whatsoever, and you can see that on the right, where if you have a sample size of 500, you can definitely see that there will never be, or very seldom you'll find a case in which you will find a difference between the groups that isn't there. But for lower sample sizes of 10 or even 20, you can see that the distribution shows that in some cases you would find some differences between the groups, even though there isn't any difference between treated and untreated. But the thing is, this poses the question, how many animals should I use? Well, not more than necessary, but you will need actually to do a power calculation for your study. And this requires you deciding what is a true meaningful effect size. This is from my own research. Actually, rather than suggest, there was guidelines in 2007 and later in 2010 for the ALS community, because as I showed you, they had reached the consensus that there was a reproducibility problem. So they issued guidelines on how to perform animal experiments especially on the mouse model that was available at the time. And this was a very well-known mouse model. So they did recommend power calculation, but because the phenotype and the variability of that model was more or less known, they proposed as a bare minimum the use of 24 animals per group, 12 males, 12 females. So 24 treated, 24 untreated. And we reviewed 569 studies, and this is the subset that was, we divided them into proof of concept and preclinical, and this was the subset of 105 studies reported to be preclinical, so held to higher standards to inform clinical studies. And what we found was that in most cases, the overwhelming majority of cases, group size was below the bare minimum recommended in the guidelines. So guidelines are useful, but if we don't follow them, if there is no system that will actually enforce them, what are they good for? If peer review fails in this regard, what can we do? And most experiments are underpowered. Catherine Button found, and et al. Found that the median statistical power in neurosciences range between 8% and 31%. This is outrageous, because this means that if there was any effect to be found, the chances of the scientists finding that effect would range anywhere between 8 and 31%. And yet they found it to the point that they reported it. Let's take this example. You can do this in GPower very, very easily, a simulation. Let's say that we are seeking 30% increase in survival. there is an observed standard deviation of 40%. So you power your experiment for 80% and alpha 0.05, and the recommended group size will be of 23 animals to have this 80% power. Of course, this is 10. This is the standard group size that one sees in, if lucky, in many published papers. And this means that for these conditions, which I think are pretty reasonable, quite sensible, you would have a 50% chance of finding an effect, which means a 50% chance of wasting the animals by not finding an effect that is there. So we do need more power in our animal studies. So what is p-hacking? I think we should start by listening to Richard Feynman, who said the first principle is that you must not fool yourself, and you are the easiest person to fool. So p-hacking is reanalyzing a data set in many different ways, or even reanalyze with additional replicas, which is malpractice, of course, until you get to the desired result. And it works more or less like this. You have your results, you perform your analysis. Oh, I have a p-value below 0.05. Hooray, let's publish. But what happens if you don't? Well, actually, you should reframe your hypothesis, do another study if you think, okay, so something might have worked differently than expected here. Maybe we should do it again, or do another hypothesis. But more often than not, we are guilty of p-hacking. So repeating the experiment to increase the sample size, rather than treating it as another experiment, analyzing just part of the data, the one that fits our hypothesis, including more variables, adjusting data by dividing by weight or transforming our data, removing the suspect outliers, choosing another group as the control. Of course, this would mean that a reframing of your whole experimental hypothesis, comparing a different dependent variable, one that gets you the p-value below 0.05 rather than the one that you had originally stipulated, or use another statistical test. Oh, we don't get a p-value with this test. Let's try the other. We are all guilty of this. I think the important thing is to be wary of the fact that this is actually p-hacking. Oh, can I transform my data? Yes, of course. Some data must be transformed before the analysis. But if you transform your data because you didn't find a p-value to your liking, then it's p-hacking. So as Ronald Coase says, that if you torture the data long enough, it will confess to anything. Which leads us to hacking. So what is hacking? Hacking is like moving the goalposts mid-game. So it's the equivalent to cheating. Hacking means hypothesis after the results are known. So rather than say, we were wrong, let's offer potential explanations why we were wrong and what this data is telling us. Let's do another experiment to confirm a new hypothesis. Hacking is going, well, our original hypothesis was quite actually another one based on the data. So this is shifting the goalposts. This is equivalent to cheating, and it is unacceptable. So there are multiple causes of poor reproducibility in the research pipeline, from the generation of the hypothesis to the publishing. And hacking will be here when you do the interpretation, and on top of p-hacking, you may actually, well, the data tells us something different, and this was our original hypothesis to begin with. Not much time to cover p-values and false positives, just that, of course, you all know that in hypothesis significance testing, alpha will be the probability of rejecting a true null hypothesis, meaning will be the chance of finding a false positive. But p-values are the probability of obtaining an effect at least as extreme as the one in your sample data. So it's a measure of how surprising your data would be if there were no effect. So it's a conditional probability. and a probability of your data, not of your hypothesis. Of course, one tends to think that, and to a large extent, truly, that the lowest the offer is set for deeming an effect significant, the less likely you will be making a fool of yourself by claiming a false positive as being true. So some authors have claimed that a p-value anywhere between 0.01 and 0.05 means little more than worth a second look. There's actually a paper on this with very relevant authors. And the too long didn't read version is that don't use P05 as a threshold for significance, but rather P005. I think this will, in theory, lower the chance of people finding or claiming to find an effect that isn't there, so type 1 statistical error. But in my opinion, it fails to address the main problem, which is the misrepresentation of what p-values actually mean. They are not the probability that the study hypothesis is true, nor the probability that you made a type 1 error, nor the probability that an absurd effect was produced by random chance. And I've seen this last one in textbooks. But I also know of cases where it was in textbooks and the authors changed it afterwards. Most importantly, a p-value, a small p-value, will tell you very little about the size of the effect or the importance of the results. So it's not a good measure of evidence regarding a model or hypothesis. It is a probability of your data. So it's basically a result of the interaction between variance of your sample, the sample size, and the effect size. And if you change any of these parameters, you can get a small p-value with actually not having a relevant effect, or the other way around. Let's see this example. Here you see these bars. The difference between the two groups is real, but is really small. You would have to really make an effort to find that the bar on the right, the light one, is actually a bit higher in whatever unit. So this is just a simulation. But if you have very low variance, you might get a very small p-value, even if your sample size is small. But if you only have low variance, as you can see in the error bars, for this small sample, your p-value will be higher than 0.05, and you won't deem these differences as significant. But if you have the same amount of variance, but you up your sample size, then the p-value becomes significant again, and the difference is the same. So one is significant, the other is not, the other is, and this is the actual difference. If you were testing a new drug against an old one, and the old one is cheap because the patent has expired, and the new one comes with a new patent and it will cost substantially more, would you actually take the new drug and buy 10 times more for the new drug in terms of the difference of effect compared to the old drug? So mind the effect size and whether that effect size is clinically or biologically meaningful. This is just to show how this was done. So as Andrew Vicker said, a mistake in the operating room can threaten the life of one patient. A mistake in statistical analysis or interpretation can lead to hundreds of early deaths. So it is perhaps odd that while we allow a doctor to conduct surgery, only after years of training, we give SPSS to almost anyone, yours truly included. I was given data to analyze and the software to analyze the data before I even had any good grasp on how to do it properly. Another problem is having too many comparisons. So this was published by Bennett et al. And they highlighted how important it was to correct for multiple comparisons, because if you do enough comparisons, you will find differences. In this case, these were the comparisons on the cerebral flow between 1,000 brain regions in the salmon brain. And even with a p-value, with an alpha set for 0.001, to deem any difference as significant, and this was really strict, they did find 2 significant spots and differences between cerebral blood flow. The problem was the experimental animal was a dead salmon. They did this for fun because they wanted to test the functional MRI machine first. So they tested watermelons and all kinds of things, but they raised a very good point in this. So having one control and many treatment groups, to have the healthy, the disease group, the disease plus treatment A, the disease plus treatment B, and then you combine with multiple outcomes and multiple time points, and you do not correct for multiple comparisons, chances are just by random variation alone, you'll find a quote-unquote significant effect. But the thing is, what was your original hypothesis? What were you trying to find out? This is the most important, because any comparison that you do, any test that you do, any group that you put in your experimental design has to reflect your experimental question, your hypothesis. Were you trying to compare disease groups versus healthy, treated versus disease, comparing different treatments? Because different choices will imply different scientific questions. Doesn't mean that they are intrinsically wrong, but they have to answer very well-defined research questions. And of course, one has to correct for multiple comparisons. There are lots of unaccounted errors and biases that I can't possibly cover here. So selection bias, performance bias, detection bias, attention bias, that deemed as the more prevailing, but there are plenty more. So sex bias is in just one sex of animals, Y. Poorly designed controls, comorbidities that either should be there and aren't, or shouldn't be there and are. Stress and distress as a confounding factor in animal research. Defining the wrong experimental unit. So defining, for instance, the animal as the experimental unit when it's the cage, when you give the treatment to the cage, meaning that you cannot assign the treatment independently to each animal. There is reporting bias, so reporting just part of the data, and undisclosed conflicts of interest. So quick answers to this: for selection bias is randomization, to performance bias is allocation concealment of the treatment groups, detection bias, blinded outcome assessment. So these are the very basic standards one should abide to. Reporting reason for excluding animals if animals do go missing. Sex bias, of course, use both sexes, use sham treated controls for and to improve animal models that they have better construct validity, so that either if there is a comorbidity of interest, the comorbidity is there, and if there is any comorbidity that shouldn't be there, it should be removed from the animal model. Minimizing stress and distress by refinement, mining cage effects and litter effects in our design for tackling the wrong experimental unit and the pseudo replication that comes with it. Publishing negative results, and of course disclosing any conflict of interest to deal with undisclosed conflicts of interest. There are many others that are specific to each experimental context. So animal studies are poorly designed. This was a comparison between systematic reviews of papers published between 1998 and 2008 and 11, and you'll see that even though there is an improvement, very few still reported randomizing of treatments to animals and blinded assessment of outcomes. So the chances of bias being there is quite high. Very low justification for sample size calculation, almost inexistent. And from conflict of interest statement, it did improve a bit, but it's still below 30% for this case. And in my own research, I found that for the ALS case, and we reviewed 569 ALS mouse studies, we found random assignment of animals only reported in 13%, and blinding of observers only in 25.7% of cases. and only 10 out of 569 justify the sample size. And in 4 of them, the justification was a bit shady. And in another systematic review performed by this lab, we were covering 124 mouse and rat studies on type 2 diabetes. We did find an improvement in reporting of random allocation of animals to treatments. So it was half of them roughly, but only 3 papers justify the sample size. This is what I see as the main problem, because no one is justifying the sample size. Why? Because in some cases, at least this is my understanding, they just don't know. Their supervisor tells them to use 10, or they see that everyone uses 10 or 8 or less than that. And the median group size was 8 for rats and 10 for mice, so just reflected convenience rather than anything else, because if anything, one should use more rats, because rat strains tend to be outbred, whereas mouse strains are mostly inbred. So there is more inter-individual variation in rats, so one would expect more animals per group to be used for rats. So how do we tackle this? Well, by planning, pre-registration, and proper reporting. For planning an experiment, I couldn't recommend the PREPARE guidelines enough. They were prepared by Dore Kopa and the RSPCA and UFO. And basically, they were inspired on the precision and high replicability of flights by airline pilots. And the pilots use checklists before takeoff, even in routine flights, and it's good that they do, because there is no point in going through the checklists after the plane lands. It has great focus on teamwork, communication between all those involved, including the people at the animal facility and their coordination. To improve reproducibility, one should also fully embrace open science. And open science, which is definitely the future, is open data, open protocols, open software, open everything. It's not stating in your paper, data is available upon request. Most often than not, it isn't. Have you ever tried? So these are just a few examples of my own papers. So actually putting my work where my mouth is, where I published a number of data sets, either supplementary materials or on database system where I could repository where I could put it where people can actually access the data and do their own analysis. And pre-registration is meant to prevent harking. So you establish your research hypothesis and your methods prior to carrying it out. You put a timestamp on it, you seal it, and you can do that on several platforms now. The OSF, but I tend to recommend the Animal Study Registry because it's tailored for animal studies. I have actually there's 2 here, but I actually have already 3 pre-registered studies, and you can already check one of them because the embargo time is over. And the idea is to prevent selective reporting and harking, and actually can avoid you getting scooped. It will increase transparency, reliability, and trust on the scientific research process, and aiding in planning for better research. So you have to prepare your protocol in advance, think things through, and then pre-register your protocol in one of these platforms. So the Center for Open Science or the Animal Study Registry. And of course, reporting enough details in experimental data. There are plenty of guidelines on a number of fields for animal preclinical studies. The ARRIVE are more prevalent. We've all have heard of the ARRIVE guidelines. There are now the 2.0 ARRIVE guidelines, which are divided into the essential 10, that 10 things you definitely have to report, and a recommended set of things you should report. Do bear in mind that the ARRIVE guidelines do not provide guidance on how to plan your experiment, how to design and carry out your experiment, on how to take care of animals. on what is clinically, biologically, or meaningful hypothesis and results. So they can point to what factors are relevant when planning, executing, and analyzing animal studies, but as reporting guidelines, they are best at listing what should have been done. As Adrian Smith usually points out, there is no way of improving a bun cake by reporting it better. Very final note, which I tend to call the elephant in the room. Doing proper experiments with greater chance of reproducibility may lead, 1, to fewer papers, 2, to less sexy results. We should do it nonetheless. Because our mission is not to publish in top journals. Our mission is not to find small p-values. This is not our business, but to produce sound, reliable, reproducible science. Science is a way of finding what is real. If we cannot be trusted to do this job, public support of science will decrease. Has it been decreasing as of recently and for a while now? Most scientific projects are based on previous and often biased results, so this perpetuates the problem, causing a vicious cycle. So we should choose between perpetuating this vicious cycle or contributing to a new virtuous cycle. So don't forget, scientists do it repeatedly. Thank you.